So, welcome to Chapter 6, Elements, Atoms, and Atomic Theory. This PowerPoint is simply an attempt to zip through Chapter 6, which you'll be pleased to know is essentially just a review of the chemistry in Science 9. So, hopefully it's not going to take you a whole lot of time just to bring you back up to speed. I'm going to just zip through the PowerPoint. The idea is you finish off 2 or 3 study guides, a couple of worksheets, and then we get to move on to new content. So the idea here in a flipped classroom is that I will basically present the information, the content, make it available to you in PowerPoint, study guides, videos like this one, and then hopefully class time is more available for you working on labs, various assignments, and hopefully you asking me questions or getting individual help. So we'll see how it goes. So as I said, elements, atoms, and atomic theory. The main ideas here are that matter is made up of atoms. Every element has its own unique type of atom. And again, elements are identified by names and chemical symbols. Nothing new there. If I give you the name silver, you immediately think of the symbol, capital A, lowercase g. Argentum. Atoms have a structure that determines their properties. Again, this is a huge concept that gets carried all through the chemistry in Science 10, that those valence electrons, those electrons in the outer shell, will actually determine the chemical reactions that an element undergoes. So, structure is important. Every atom is composed of 3 types of subatomic particles. You've heard of them before. Protons, positive. Neutrons, no charge. And electrons, of course, negatively charged. The number of electrons in the outer shell of an element's atoms determines the properties of the element. Hugely important concept there. I'm going to read it again. The number of electrons in the outer shell of an element's atoms determines the properties of the element. So, if you look at the Bohr diagrams for calcium, neon, nitrogen, and magnesium, notice that neon, which is a noble gas, has 1, 2, 3, 4, 5, 6, 7, 8 outer shell electrons or valence electrons. These are all noble gases. They are very unreactive. They are stable. There's no tendency to either lose those electrons or gain electrons because of something called the octet rule. They already have a full outer shell. Why lose them? Why gain them? In a sense, you could say that every other element is trying to become like one of these noble gases. On the other hand, take magnesium, 1, 2 outer shell electrons. Calcium, 1, 2 outer shell electrons. Again, calcium and magnesium are both members of the same chemical family. They're members of the alkali metals. And the reason they're in the same family, you guessed it, they have the same outer shell structure, which is going to determine their properties. Easy. So, in case you missed it, key ideas in Chapter 6. Matter is made up of atoms. Thank you, Democritus. Atoms have a structure that determines their properties. Those electrons are important. And then, based on those outer shell electrons, the periodic table is organized. And the periodic table is ever so useful. Make sure you actually have a copy of this PowerPoint. I've done the nasty teacher thing and actually whited out certain words just to help you kind of follow along as we go. And yeah, in the process of writing out some of these key words, hopefully your brain says, yeah, that's important. Also, get very used to either having your own copy of the data booklet for Science 10 or access the data booklet either online or from the school network, because that data booklet is something that you'll be given on the provincial exam. And hey, better to look at the periodic table that you're actually given than worry about a periodic table that suddenly gets thrown your way that you've never seen before. So, to begin with, 6.1. Again, remember, this is Science 9 in review. Real quick. Properties are used to identify matter. There's different types of properties. Physical properties can be observed without changing the chemical structure of a substance. On the other hand, chemical properties describe a possible chemical change. Okay, if I was in class right now, I'd grab a piece of flash paper and I'd rip it in half. Physical property. I could actually describe that it's a solid. I could describe its white color. But once I light that piece of paper, you're going to see this flash of light, heat given off, and poof, there's nothing there. Well, of course, there is something there, but you don't actually see those gases. In other words, these chemical properties aren't reversible. The physical properties are theoretically reversible. So a physical property like melting, a change of state, not a chemical property. Burning, combustion, oxidation, all those type of things are actual chemical properties. Matter, you are made of matter. You matter too, but hey, matter is made up of atoms. Atoms are the smallest particles of each element. Elements, compound, and mixtures together make up all matter. Mixtures are made from two or more substances that are not chemically combined. Think of raisin bran. You can actually pick out the raisins if you don't like them. Physically distinguish characteristics in a mixture, whereas in a compound is a pure substance like an element. You aren't going to be able to identify in a solid piece of sodium chloride where the sodium is or where the chlorine is, because you've actually had changed chemical properties. Elements are identified by names and chemical symbols. Once again, let's do gold this time. Well, I guess we need a pen, don't we? Pen, yeah. Let's go for an ink color. Stick to purple. I like purple. So again, a symbol, AU. Latin aurum tells you, of course, that we're talking about gold. And then some elements are actually found as paired atoms. So these are the diatomic atoms. The sooner you recognize which ones are diatomic, say I tell you that chlorine reacts with something, you should get used to the fact that chlorine is always going to be diatomic. 2 atoms of chlorine per molecule of chlorine. Same thing with oxygen, diatomic, O2. Hydrogen is H2, Br2, iodine, I2, and I'm running out of room, but basically the halogens, they are diatomic. 6.2, atoms are made up of component particles called subatomic particles. They include protons, neutrons, and electrons. Every atom of any one element will have the same number of protons. If I say sodium, you immediately know we're talking about sodium. If I say that it has 11 electrons, you know we're talking about sodium. If I say it has 11 protons, we know we're talking about sodium. So that atomic number identifies the element on the periodic table. So positive protons and neutral neutrons are found in the nucleus. Again, the nucleus is made up of positive protons and neutral neutrons. Negative electrons are arranged in outer shells or in orbits around the nucleus. There are an equal number of protons and electrons in a neutral atom. Again, we have these things called ions. Ions form when the number of electrons change. So normally if you look at a periodic table, you're not talking about any element that has a charge. An element only becomes charged when they lose these outer shell electrons, and they will lose certain numbers depending on which element we're talking about. So an ion, very important word. If one of these electrons is lost, we will have a 1+ ion. If 2 of them are lost, we'll have a 2+ ion. Why is it plus? Because electrons are negative. If you lose 2 negative things, you're actually gaining positive charge. If, on the other hand, an element gains an electron, we would say it has a -1 charge because it's gained something negative. The number of electrons in the outer shell determines the properties of the element. That's important. Yeah. 6.3, classifying elements with the periodic table. Elements can be classified or grouped in many different ways using, again, physical and chemical properties. The groups include metals, nonmetals, and metalloids. Some groups of elements have characteristic sets of common physical and chemical properties, and they are called chemical families. So this lovely periodic table down here shows you the chemical families. And just in terms of organization, basically the metals are found on the left side, all the way from here, group 1, all the way to the zigzag line. are essentially metals, and they become more metallic as we go left, more metallic as we go down. So francium is much more metallic than, say, manganese, and it's even more metallic than cesium. So metals are found on the left side, nonmetals on the right of the zigzag line, and right along the zigzag line we have the metalloids with properties and characteristics of metals, nonmetals. Chemical families are arranged in vertical groups. So these are the chemical families, the vertical groups. These horizontal rows are called periods. Period 1, period 2, period 3, you get the idea. So the table can also display the chemical symbol, atomic number, atomic mass, ion charge, density, and other information. Make your periodic table your best friend. For now, make sure you know the names of these families. The alkali metals, group 1, alkaline earth metals, group 2. Transition metals are basically transitioning from 12 through 3, becoming more metallic, and some of them have different combining capacities, different charges. More to be said about that in the next chapter. We have the rare earth metals down here, which are really stacked cards below these two. That's why they're down here. Otherwise, we'd have this incredibly wide periodic table. Just wouldn't work for books, etc. The halogens, fluorine, chlorine, bromine, iodine, etc., very reactive, and they're very reactive for a reason. They are lacking one outer shell electrons, and they really want to become, like their neighbors, the noble gases. Everything in the noble gas family has a full outer shell. They're inert. They really don't want to react with anything. Got to be careful saying that things don't want to. It's kind of a case of anthropomorphism. We're saying that these non-living physical objects have a tendency or a desire, and of course that's not quite true. There's an actual reason for them wanting to become stable. And here I am using the word wanting again. So when you look at a periodic table, you should be able to immediately recognize the information there. The atomic number, again, defines the element. There is no other element that has atomic number 80. If I say atomic number 80, you know we're talking about Hg, mercury. This information here, boiling point, melting point, density, not terribly important in this course, but obviously in university, where you get to, say, make some of these compounds, then it becomes important. When you write compounds, formulas, you really need to know the common ion charge. The most common one is usually on the top. Then there's a lesser common charge. More to be said again about that. Chemical symbol, the name, and then down at the bottom, notice the atomic mass. If I don't really do another one of these little presentations on isotopes, make sure you look at the links on Dunamis that cover the isotopes, because you really need to know why mercury's atomic mass isn't a whole number. Why is copper's atomic mass not a whole number? And the reason is because we have different isotopes of a lot of these elements, where one of them has a certain number of neutrons and another has a certain number of neutrons. So what you get here is the average atomic mass, and yeah, that becomes important. When you're trying to determine how many neutrons are in an element, by the way, what you're trying to do is round this to the nearest whole number. So in any calculation, you wouldn't use 200.6, you would actually round that to 201. So this is where you actually get to see if you know what you need to know. So there's something called mass number, not to be confused with what we just looked at, the atomic number. Mass number is the total number of protons and neutrons. So you're adding protons, which are the atomic number, and neutrons to get the mass number. How you write that is by, notice this lithium 7. So 7 tells you some information. It tells you that it has a mass number of 7. And in order to know how many protons, you basically have to look at the periodic table. If you look at the periodic table for lithium, you'll see that it is 3. So you know you have 3 protons. You also know it has 3 electrons, by the way. The question is, how many neutrons? In order to determine how many neutrons, take the mass number and subtract the number of protons. 7 minus 3 equals 4 neutrons. And as I said, in a neutral atom, the number of electrons is simply going to be equal to the number of protons. So you try it. This is where you might want to just stop the video presentation and see if you can tell me what the mass number of bromine 79 is. Then you can tell me what the number of protons are, number of neutrons, and number of electrons. Try it. Okay, I'm going to assume you've tried it. What is the mass number of bromine 79? Well, when you see bromine 79, that tells you already that the mass number is just the number given there, so it's 79. Number of protons, you got to look at the periodic table. Bromine's atomic number is 35. So that's the number of protons. That also tells you the number of electrons. How do you find the number of neutrons? Take the mass number and subtract from it the atomic number. 79 minus 35, let me think about that, 44 neutrons. Right. So there's a couple of things left in Chapter 6. Basically, you already wrote in Science 9 a whole lot of Bohr diagrams for the first 20 elements. It's probably not a bad idea for you to do the same thing again. So there's a Bohr diagram assignment, and then there's just a wee little assignment on you doing the periodic table. So in case you wonder what those are, this was the Bohr diagram for the periodic table, and I don't think you'll have any problem with it. For instance, if you just start on the far left, we're talking about hydrogen, 1 proton, no neutrons, element number 1, element symbol is actually what they're looking for there, and it is atomic number 1. Just below hydrogen, you will have, of course, lithium. Lithium, if I'm not mistaken, has 3 protons, and it has 4 neutrons. Round off the atomic number, or atomic mass, and subtract the number of protons to get the number of neutrons. So the element, I said, is lithium. Atomic number, of course, is 3. Just to make sure you got this, the next element below lithium in the alkali metals would be sodium. And sodium has 11 protons. And how many neutrons? You take the atomic mass, subtract 11 from it, you should get 12, as long as you rounded it up to the nearest whole number. And again, what they want you to do with all of these is take the electron shell. In the case of hydrogen, you've got 1 outer shell electron. In the case of lithium, you've got 3. So always 2 in the first shell, and then begin to fill up the other shells to a maximum of 8. So do we want to put 11 in here for sodium? Nah, you'll get bored, right? So, yeah, if you have any problem with that one, see me. Same thing with this one, analyzing the periodic table. I would leave this one to last because until you've done study guides 6.1, 6.2, and 6.3, you probably will take too long on this, right? So don't start off with this one. This might be the culmination. And then we have this wonderful thing called a Chapter 6 test.